Hi, welcome to our Stats. I'm Jacob Cybulski. In this series of videos, I'm going to introduce you to some predictive statistical models, such as naive Bayes and regression, with plenty of data visualization. Welcome back. Welcome to this mini-series on regression modeling in R. In a previous lesson, I showed you how to deal with multiple variables, how to select those variables, eliminate extreme values, and deal with multiple collinearity between variables to arrive at a good quality model. And I'm going to follow from that to show you how you could visualize data which spans multiple dimensions. And it's useful especially for multiple regression. We're going to use the same data as before from the UCI University on automobiles, where we try to predict the price based on the car specifications. So I'm not going to spend much time explaining it. For explanations of how to construct the model, refer to the previous video. I'm going to use 3, 4, 5 libraries which will help me deal with those problems. Let's get the data in, isolate the variables and eliminate the missing values, create a data frame, and transform two heavily not normal variables, split the data set into training and validation set, and eliminate extreme values, which was quite a long process, but eventually I arrived at those particular instances of observations, and I remove the by row names. Eventually we created the fit, which behaved well and which had no multiple collinearity as evidenced from the function VIF. Okay, so that was very quick. Let's get a subset of the data for exploration, and we can see the first visualization that you're familiar with. It's a correlation plot which shows the relationship between the price, curb weight, and peak RPM. Now we can do better than this and visualize more information about those variables against the fit, and therefore have better understanding of errors around the linear model. The first approach to visualization will be to fix one of those variables. In this case, the peak RPM looks like it's a bit of chaotic and dispersed, so we'll fix the values in this particular variable and observe the impact of that value on the relationship between curb weight and price. So I'm going to select 5 specific values from the range of possible values for peak RPM, from the minimum to the maximum. So take the minimum, first, second, third quartile, and the maximum. 5 values. I'm going to isolate them, take them out of the summary table, and store them as numeric values in 5 different variables. What I'm going to do next is to create a range of possible values from the second variable, which is curb weight. And I observed that the curb weight varies from around 1400 up to 4100, and therefore I created 100 values in that range and stored it away in the vector CW range. Now I'm ready to play with this. Let's recall and let's create the first fit. I'm not going to do the second one. And let's predict the values for different specific values selected for the peak RPM, while varying the remaining 2 variables. So I'm trying to predict the price, and I'm going to use the other 2 variables for that prediction and creating a new vector for each of those specific values of peak RPM. Now let's plot all of them. So I'm plotting 5 lines against a range of data points in the data. Okay, here we are. As you can see, when we have the lowest possible value for the peak RPM, it actually has the lowest predicted price. The highest value for the peak RPM, it corresponds to the highest predicted price across all ranges in peak RPM. So it's a first way of having a look at it. Also, we can see that the lines are parallel. Often when you do that, you can see the lines will be intersecting. It also means that there's a good linear dependency between the curb weight and price, and it's a very linear dependency. Okay, let's fix one issue. As you can see, the y-axis has very small values. That's because at the very beginning I did a log transform of the price. So this is actually logarithmic transformed set of variables. Let's fix it by producing the plot where the price is actually, we do inverse transformation of the price, and this is done across all values. And now you can see that we have the y-axis is pretty much in the correct units, but that had effect on the linear model fit. Is no longer linear, it's logarithmic. That's because it's actually it's exponential here. That's because we applied the back transformation. A good question at this point is, can we trust that this data is really linear at all levels of the peak RPM? Well, to answer that, we're going to repeat this, and instead of using a simple linear model, we're going to use Loess model, Loess polynomial fitting of data. So let's recalculate all the predictions, and let's plot initially in the transformed units. We have some data outside this range, and interesting things happen here. The blue line corresponds to the lowest level of peak RPM, and you can see that in the mid-range it's as good as the highest revving engines on cars. Later on it drops off. That means the low revving engines will produce the lowest predicted price. But the most interesting is the red line, which is the engines which rev very fast. Those cars, it looks like, at the lightest cars, the curb weight here is the lightest, they're the cheapest. You may have seen some cars which sound like a lawnmower. They're small, they rev fast, they're cheap, and they're not very powerful, so they have the lowest price. You can see there's not quite a linear dependency across all levels of peak RPM in cars, and that's evident from this plot. And of course we could do the correction of the price units, so at least we can see the y-axis in all its dollar glory. It's a bit harder to read, and that's why we need to have the next type of plot. We use Coplots, which allow us to split this type of chart into several charts. Here we fixed the price, we fixed the value of one of the variables, peak RPM, and observed the other variables and how they relate one to another. What if we wanted to see the whole range of values in the third variable? This is where Coplots come to help. So we have here a function which will be helpful in creating the Coplots. That function simply plots the contents of several possible plots. Here we have 6 panels. The 6 panels which are guided by the value of peak RPM variable, which is conditioning variable for the Coplot. The system identified different ranges of peak RPM which are worth grouping and plotting as separate charts. So this bar, which corresponds to the lowest range of peak RPM, is represented here as a relationship between curb weight and price in that range of peak RPM. The next bar at the bottom corresponds to this chart, the third corresponds to the third chart, and then the third from the top corresponds to the left top chart, middle, and finally the longest bar to the right top charts. Each one of them has more or less the same number of points, and they do overlap indeed. As you can see, this bar and that, they overlap in peak RPM values quite significantly, and so they're very similar here. So this is a way of getting a glimpse into your data across ranges of the third variable when you limit it to two-dimensional representation. However, lucky for us, we're dealing here with 3 dimensions only, and of course 3 dimensions can be visualized easily on a 2-dimensional monitor. And so we turn to the third function, scatter 3D. The help is shown here, which allows you to plot x, y, z coordinates. So let's pick curb weight, peak RPM, and price against each other from the original data. The data in which we simply removed missing values. Let me bring the plot up. This is the data, the price, peak RPM, and the weight, and the blue plane represents the linear model. The yellow dots represent the observations, and the green lines the distance to the model. We can actually move this chart to observe it from different angles. We can see that the original data was quite far from the linear model, which was constructed for this data set. Quite interesting. Let's look at 3 other variables. We rejected horsepower as the variable for the linear model, and also the city miles per gallon. Let's see how they compare in 3D. You can see that horsepower and city miles per gallon, we have huge extreme values, and a lot of them in this case. So that probably wasn't a good triple, and we can see it by visual inspection. And let's look at the third combination, horsepower, curb weight, and normalized losses, if in case we wanted to predict normalized losses based on the weight and the horsepower of the car, the losses on insuring the car. And you can see here the data is all over the place. The data is very, very far away from the regression plane. So we made the right pick, and there was a process to it. Now let's look at the effect of cleaning up the data in the model, starting from the raw data and then selecting the data which had no collinearities and which had no more extreme values. I'm going to restrict viewing the data to the final training set so that we compare same with same. So the first plot is what we got. However, this is the data where we had collinearities and extreme values. And two variables were not transformed, so they were not normally distributed. This is the effect of transformation of price into logarithmic transformation of the price. And you can see not much changed, but the units of the price changed. So now it's a unit from 0 to 5, and so a lot of dots must have been squashed a little bit. Finally, when we got rid of extreme values from the data set and created a linear model, we have a very nice set of variables which are hugging the regression plane, and that's why we used it eventually as the plane which gave us the minimum overall error. Now we could use the same technique for the creation of a similar effect that we started with when we fix one of the variables and we look at dependencies between the others. Here I have only 3 variables, so I'm going to use the price as the variable to group the relationship between two other variables. So I'm going to create a class variable based on the price, and the brackets will be 1000 up to 30,000 and above. I'm going to also create a similar split for the training set, so I'm going to show you the raw data and the data which was corrected through the cleaning up of the regression model. So 2 class variables, and let's look at the first plot. As you can see, I create a model in the original data set, and the grouping will be by price categories. Let's look at this. You can see we have 3 planes. We have 3 groups of observations which belong to 3 categories of prices. And you can see the top one, we have the least observations, the least cars, lots of cars in the middle, and less in the bottom range of the price. So that was a nice representation. Let's look at the view of the data after it was cleaned up and the model was most effective. Not much changed. You can't actually assess it visually because the price is squashed. Maybe it's less readable. So visual inspection is not always the best way of assessing the model performance. Let's look at creation of Loess plane fitting here. The original data. You can see that the regression planes were not actually fitting the data well. So this is actually a 2-dimensional fit of 3-dimensional data, and you can see those planes are very deformed. So there's a lot of nonlinearity in the data and the models. Let's see if it improved after we created a better model. You can see perhaps that the data has been better separated. There's less overlapping between the sections of the data. Of course, when the the data sets very close, there will be a close overlap. There is a slight improvement in the distribution of data, and those hyperplanes are not so much deformed. Finally, we could use the class grouping to actually group the data and see the groupings. So you can see the data is grouped into sort of spheres, and you can see the groups are sort of non-linearly distributed, and the groups, the direction of the groups is twisted in at least 2 dimensions, or three dimensions here. What happens when the data was eventually improved and cleaned up and the new models created? The groups are more lined up in 3-dimensional space. So the very top group, it follows the same direction more or less as the other 2 groups. So this is just a visual inspection of groups of data, data distributed in 3 dimensions. If we have more than 3 dimensions, then we're back to similar techniques that we showed before. We need to fix the values for 1 or 2 or 3, either in ranges of the variable values, or picking a specific value and observe the effect of those on the remaining variables. So a bit of 3D data visualization and 2D visualizations of multiple dimensions on 2D in color. Thank you very much. Good luck. Enjoy plotting of your linear regression.